Hi everyone. In this video, we will talk about towers of function fields. So let's begin with the definition. So recall that a tower over Fq is an infinite sequence of function fields Fi, where each Fi is a function field with constant field Fq, such that each Fi is strictly contained in Fi plus 1, and each extension Fi plus 1 over Fi is finite and separable. And the sequence of the genera, Gi, which is the genus of Fi, tends to infinity as I tends to infinity. And remember that we have the following remark, which we saw in class, which says that if F0 over Fq is a function field, and we have a sequence of finite and separable field extensions, then in order to show that this sequence is a tower, it suffices to check two things. So the first is that there exists some index j such that the genus of fj is at least 2. And for each index I, there exist prime divisors pi in fi and capital Pi in fi plus 1, which lies above pi, such that the ramification index is equal to the degree of the extension, and it is bigger than 1. Then we can conclude that the sequence is indeed a tower of Fq. So if you recall, so for example, this inequality here implies that Fi is strictly contained in Fi plus 1. So the first condition indeed holds for all I. The fact that all the extensions are finite and separable is just part of the assumption here. The first condition here guarantees that the sequence Gi tends to infinity, and the fact that there exist such places which are ramified guarantees that Fq is indeed the constant field of each Fi. So for a specific index I, existence of such a Pi and capital Pi with E greater than 1 guarantees that the constant field of Fi is Fq. Okay, so a few more definitions. Recall that if F is a tower over Fq, then we denote by Ni or Nfi the number of prime divisors of degree 1 in the function field Fi. And then we define the splitting rate of the tower by the limit, the following limit, Ni over the degree of the extension Fi over F0. The genus of the tower is defined by almost the same limit, but this time with Gi in the numerator instead of Ni. And the limit of the tower defined by lambda f, which is the limit of Ni over Gi. And we say that the tower is asymptotically good if lambda f is positive. And remember that we saw in class that all these limits exist. The splitting rate is even finite and non-negative. The genus of the tower is positive and can be infinity. And the limit of the tower is equal to the quotient of these two, and it is finite and non-negative. And it's also easy to see that the tower is asymptotically good if and only if the splitting rate is positive and the genus of the tower is finite. And remember that what was the motivation for this definition? When we analyze the AG codes in terms of rate versus distance, we saw that the sum of the rate plus the relative distance is at most 1 minus some loss. This loss was essentially Gi over Ni, Gi minus 1 over Ni. So it was the inverse of this quantity. So if we want good codes, we want this lambda to be as large as possible. So this is why when it's positive, we call the tower good, asymptotically good. So the hope is to find tower in which lambda f is as large as possible. And now you may ask, what is the best that we can hope for? And the answer is given by the theorem of Drinfeld-Ladut, which says that if f is a tower over fq, then lambda f, the limit of the tower, is at most the square root of q minus 1. So we have this upper bound. So when we build codes from towers, then we always get a loss, which is at least 1 over the square root of q minus 1. But still, if we can achieve this capacity, then at least for some q's, for example, q which is 49, this loss is better than the loss in the Gilbert-Varchamov bound. So now the challenge is to find good towers, or even optimal towers, if that's possible. So what we are going to do next is to give a concrete example of an optimal tower over the field F4. So this is going to be our example. So let's consider the tower T1, which is given by the following definition. F0 is the rational function field F4 x0. And for each I, we recursively define the field Fi plus 1 to be the extension of Fi when we add a new variable xi plus 1, such that xi plus 1 cubed is equal to this term, xi cubed over xi squared plus xi plus 1. So in other words, the tower T1 is the tower over F4, which is recursively defined by the following equation. Y cubed equals to x cubed over x squared plus x plus 1. And we claim that the tower T1 is an optimal tower of F4. That is, the limit of this tower is exactly the square root of q minus 1. In our case, q is 4, so it's 2 minus 1, which is 1. So we need to show that first that T1 is indeed a tower, and then to show that this is indeed the limit. So let's begin with a simple observation. So let's consider the place P infinity, the unique pole of x0 in the basic function field f0, which is just the rational function field over f4. And suppose that capital P infinity is a prime divisor lying above P infinity. Then the valuation of x1 cubed at capital P infinity is on the one hand equal to 3 times this valuation of x1, but on the other hand we can substitute this term for x1, and this element is in f0, so by definition this valuation is exactly the ramification index times the valuation at P infinity of this element. And we know that since the numerator is of degree 3 and the denominator is degree 2, then this valuation is minus 1. So overall, we get that this is equal to minus the ramification index. But of course, the ramification index is at least 1, and at most the degree of this extension, which is at most 3. But note that minus the ramification index is exactly 3 times the valuation here, which is an integer. So in particular, 3 divides the ramification index, and therefore it must be that the ramification index is equal 3, and also the degree of this extension is 3. And also this valuation is minus 1. In particular, we get that the place P infinity is totally ramified in the extension f1 over f0, and the capital P infinity is the unique prime divisor which lies above it in f1. Moreover, if we consider the extension f1 over f0, we can see that f1 is f0 together with x1, where x1 to the n is equal to u, where n is 3 and u is this element in f0. And note that n is 3, which is coprime to the characteristic. f4 contains a primitive third root of unity. In fact, every element in f4 which is not 0 or 1 is an element of order 3 in the multiplicative group of f4, which is a group of order 3. So we can take, for example, the element delta, where delta satisfies delta squared plus delta plus 1 equals 0. And moreover, the element u is not equal to w cubed for any w in F0. For example, we saw that the valuation at infinity of the element u is -1, which is not a multiple of 3. So u cannot be of this form. Therefore, the extension f1 over f0 is a Kummer extension. So it is in fact even Galois, and in particular, it is finite of degree 3 and separable. Now, remember, we saw that the valuation of x1 at capital P infinity is also -1. So it's the same as the valuation at infinity of x0. And the relation between x2 and x1 is exactly of the same form of the relation between x1 and x0, since the tower is defined recursively with the same relation. And therefore, we can reiterate this argument for all I, and conclude that the extension fi plus 1 over fi is always finite and separable of degree 3, and there always exists a prime divisor pi and a prime divisor capital Pi in fi plus 1, which lies above pi, such that pi is totally ramified. So this ramification index is exactly 3, which is also equal to the degree of the extension. So in view of remark 1, this implies that the constant field of each fi is f4. And of course, all these extensions are finite and separable, and fi is strictly contained in fi plus 1. So the only thing that we need to show is that there is some genus which is at least 2. And indeed, this is the case, and we will see this later. So indeed, T1 is a tower. So now, in order to find the limit of the tower, let us first try to analyze what are the rational prime divisors in the tower. Namely, what are the rational prime divisors, the prime divisor of degree 1, in each one of the FIs. So the first level is simple. F0 is just the rational function field over F4. So we know that the rational prime divisors are exactly P0, P1, P delta, P1 plus delta, and P infinity. And remember, delta is a root of this polynomial, so delta squared plus delta plus 1 is 0. And as usual, each rational prime divisor in F1 must lie above one of these 5. So let's explore what are the prime divisors above them in F1. So let's begin with P infinity. In fact, we already showed that P infinity is totally ramified. And we also know that F0 and F1 both have the same constant field, which is F4. And therefore, the degree of the prime divisor capital P infinity, which lies above P infinity, is exactly the residual index of this place, which is 1. Okay, let's move on to the place P1. So note that the minimal polynomial of x1 over f0 is phi of y, which is y cubed minus this term. So let's try to use Kummer theorem. So for that, we need to consider the polynomial phi1 of y, which is obtained from phi y by going modulo x0 minus 1. So simply substitute x1 for x0. So we get y cubed minus 1 cubed over 1 plus 1 plus 1. And since the characteristic is 2, this is exactly y cubed minus 1. And what is the decomposition of this polynomial to irreducible factors in the polynomial ring over F4? Then it's easy to check that, these two equality holds, and this is the factorization. And now we can use Kummer theorem, which says that for each such irreducible factor, there exists a prime divisor, distinct prime divisor lying above P1 in F1. And by the fundamental equality, we conclude that P1 splits completely. And in fact, we even know more. We know that the place which corresponds to the first prime divisor above sends x1 to 1. The place which corresponds to the second prime divisor above sends x1 to delta. And the third place, the place which corresponds to the third prime divisor above maps x1 to 1 plus delta. And therefore, we will use the following notation for these prime divisors, capital P11 for the first, capital P1 delta for the second, and capital P11 plus delta for the third one. Okay, let's move on to P delta. So suppose that capital P delta lies above it in F1. So let us first find the valuation at delta of this function. So of course, this is the valuation of the numerator minus the valuation of the denominator. And for the numerator, this is just 3 times the valuation of x0. And since this valuation is 0 and this valuation is 1, we get -1. And indeed, this valuation is 1 since this polynomial factors to x0 minus delta times x0 minus 1 plus delta. So the valuation at delta is 1. So in fact, we can proceed exactly as in the analysis of P infinity and get that the ramification index is 3. So P delta is totally ramified in F1 over F0. So capital P delta is unique. It has degree 1, and the valuation of x1 is -1. So this is just exactly the same argument as we saw for P infinity. Let's move on to P1 plus delta. So suppose that capital P1 of delta lies above it in F1. Let's compute the valuation, and exactly the same thing happens. We get that this is 0, this is 1, so the valuation is -1, and in fact, this case is also similar. So the prime divisor P1 plus delta is also totally ramified in F1 over F0. Okay, so now it only remains to handle the last prime divisor P0. In this case, if we try to use Kummer theorem, then we get that phi 0, when we go mod x0, then we get the polynomial y cubed minus 0, which is y cubed. And unfortunately, this polynomial does not have the composition to distinct irreducible factors. And therefore, we cannot apply Kummer's theorem for the element x1. However, we can consider another element. Let's consider the element z, which is x1 over x0. So z is another element in F1. And note that z cubed is exactly 1 over x0 squared plus x0 plus 1. So the minimal polynomial of z is phi tilde, which is z cubed minus this term. And now if we go mod x0, we get that phi 0 tilde is just z cubed minus 1. And this polynomial splits over F4 to this product. So now we can use Kummer theorem to get that P0 splits completely in the extension F1 over F0. So there are 3 prime divisors lying above P0 in F1, and their corresponding places map Z to the following. The first maps Z to 1, the second maps Z to delta, and the third maps Z to 1 plus delta. So let's denote these prime divisors by capital P0 Z minus 1, capital B0 Z minus delta, and capital P0 Z minus 1 plus delta. And of course, all these 3 have degree 1, and for each one of them, if we compute the valuation of x1 cubed at this prime divisor, then we get it on the one that it's this thing, 3 times the evaluation of x1. On the other end, by definition, by the relation, it's just the ramification index times the evaluation of this element at 0. And since the E is 1 and this is 3, we get that the evaluation of x1 is 1. So it's equal, in fact, to the evaluation at 0 of x0. So one important remark here is to notice that for each prime divisor above, its corresponding place maps x1 to 0, since the evaluation of x1 is positive. So for each such place, x0 is mapped to 0, x1 is mapped to 0, but still there are 3 different prime divisor above, and in fact, each one of them sends the function z to a different value. So in particular, the fact that we know that the place above sends x0 to 0 and x1 to 0 does not suffice to conclude that this place is unique. And indeed, in this example, we see that the place is not unique. There are 3, which differ by the value of z, this function. So in summary, by this, we found all the rational prime divisors in the first level in F1. So we have the following picture. So we have the prime divisors p infinity, p delta, and p1 plus delta in the rational function field in F0. And each one of them is totally ramified in F1 over F0. So for each one of them, there is a unique prime divisor lying above it in F1. And the ramification index is 3. And for the remaining prime divisor, P0 and P1, we get that each one of them splits completely in F1 over F0. And this is the picture with the notations that we suggested. So in particular, we get that N0, the number of rational prime divisors in F0 is 5, and N1, the number of rational prime divisors in F1 is 9. So this is the picture in the first level in F1 over F0. And now you can ask what happens in the next floors. So for example, if we consider the next floor, F2, the extension F2 over F1, so again, we can consider all the rational prime divisor in F1, which we've just found, and then use similar arguments to analyze the behavior of the prime divisors in F2, which lies above them. So for example, you can check that for the ramified places, we obtain that they are still totally ramified. So for example, exactly the same reasoning shows that the place capital P infinity in F1, which lies above P infinity, is totally ramified in F2 over F1. And the same for capital P delta infinity, which lies above P delta, and capital P1 plus delta infinity, which lies above capital P1 plus delta. So these 3 are totally ramified, and in fact, this continues also for the next levels of the tower. Each one of them is totally ramified all the way. So this is for these 3. And now for these 3 prime divisors, which lie above P0, you can check that each one of them splits completely in F2 over F1. For example, the first one, capital P0, Z minus 1. Remember, this is just a prime divisor whose corresponding place sends x0 to 0 and z x1 over x0 to 1. Then this place splits completely. And similarly, if we denote by w the function x2 over x1, then we get that these are the prime divisors. So the corresponding places above sends w to 1, delta, and 1 plus delta, respectively. So this place splits completely, and there's 3 prime divisor above, and the same for this one, and the same for this one. And in fact, you can verify that this keeps going also in the next level of the tower. That is, every place in the tower which lies above P0 in F0 splits completely. And finally, we need to see what happens with these three prime divisors in F1. So here you will get that the behavior is a bit different. So for example, for these prime divisors, capital P1 delta, recall that the valuation of x1 is -1. So here x1 has a simple pole at this prime divisor. So when we will analyze the behavior above, you will get that essentially it's the same thing as in P infinity. So a similar calculation, exactly similar to the one which appears here, shows that this place is totally ramified. So this place is totally ramified in F2 over F1, and the same thing is true for this prime divisor. It is totally ramified in F2 over F1. So these two prime divisors are totally ramified. And for this one, we can use Kummer's theorem, and the analysis will be exactly the same as the analysis of P1. And we will get that this prime divisor splits completely in F2 over F1. So I will leave it for you to check all the details, but using the same arguments, you can verify that this is the picture. So these two prime divisors are totally ramified, and capital P11 splits completely. And using the same notation, let's denote the prime divisor above by capital P111, 11 delta, and 1 plus delta. And in fact, we can continue in the same manner to the next level. So for example, in the third level, these two, each one of them will be totally ramified. And these two will also be totally ramified. And this one will split completely. And observe that in particular, if we consider the prime divisor P0 in F0, then it splits completely in F1, and each one of those splits completely in F2, and so forth. So we get that in Fi, there are 3 to the I prime divisors of degree 1, which lies above P0, and therefore we have the following lower bound on Ni. Ni is at least 3 to the I. Okay, so we have a good lower bound for Ni, and remember we want to find the limit of the tower, which is the ratio between Ni and Gi. So let's move on to find the genera Gi. So for this, first note that each Fi plus 1 over Fi is a finite and separable extension, and of course both Fi plus 1 and Fi have the same constant field Fq, F4 in our case, and therefore we can use Hurwitz genus formula. So we get that 2gi plus 1 minus 2 is equal to the degree of the extension, which is 3, times 2gi minus 2, plus the degree of the different of the extension. So this degree is 3. What about the degree of the different? So recall that by definition, the degree of the different is the double sum when we go over all the prime divisors in Fi and over all the capital P which lie above them in Fi plus 1. And for each pair, we multiply the ramification index -1 times the degree of the prime divisor above. But note that this extension is of degree 3, and it is Galois. So by the fundamental equality, we get that each ramification index here is either 1 or 3. If it is 1, then this is 0. And if it is 3, then this place is totally ramified. So there is a unique capital P lying above it. And therefore, we get that this double sum is exactly twice Ri, when Ri is just the number of places P in fi, which are ramified in this extension. And in this case, they are not just ramified, they are totally ramified, actually. So now our goal is to find Ri, that is the number of prime divisors in Fi, which are ramified or totally ramified in this extension. So let's try to answer this question using the additional assumption, at least for now, that every such P, which is ramified in this extension, actually lies above a rational prime divisors in F0. We will justify this later. For now, let's just assume that this is the case. And now with this additional assumption, this will be easier since we already know what is the behavior of the rational prime divisors of F0 in the tower. So we know what are the places above them and what is the behavior, where is the ramification, and so on. So let's see. So we claim that Ri is 3 plus 2 times I. So let's see. So this 3 comes from these 3 rational places in F0. We saw that each one of them is totally ramified in each level. So in Fi, there are 3 prime divisors of degree 1, which are totally ramified. Now, as for P0, we know that it splits completely in all the levels, so there is no ramification above it. So it remains to check what happens above the prime divisor P1. So in Fi, which prime divisors that lie above it are ramified. So for example, if we consider these 3, then we saw that these 2 are totally ramified. So this is totally ramified, this is totally ramified, and this one splits completely. So in F1, there are 2 prime divisors lying over P1, which are totally ramified. What happens in the next level? So these 2 will still be totally ramified, and out of these 3, 2 will be totally ramified, and the third will split completely. So in the next level, there will be 4 ramified places. So we get that in F2, there will be 4 prime divisors which lie above P1 and they are totally ramified in F3 over F2. So it's easy to see that in each level, the number of prime divisors which are totally ramified is increased by 2. So in fact, we will get that in Fi, the number of prime divisors which lie above P1 and are ramified in Fi plus 1 over Fi is exactly 2i. So overall, we get that Ri is exactly 3 plus 2i. So now we can substitute everything in equation 2 and get that 2gi plus 1 minus 2 is exactly 3 times 2gi minus 2 plus twice Ri, which is the degree of the difference. And therefore, we can substitute the expression for Ri, which is 3 plus 2i, and rearrange to get recurrence gi plus 1 is equal to 3gi plus 2i plus 1. And of course, we know that G0 is 0 since F0 is a rational function field. So we get a recurrence relation, so we can solve it and extract a formula for Gi, the genus of the field Fi. So the genus of the function field Fi is exactly 3 to the I minus 1. And note that in particular, G0 is of course 0, G1 is 1, but G2 is 6, which is at least 2. So indeed, it is a tower. But of course, if this is Gi, then obviously Gi tends to infinity as I tends to infinity. Finally, we get that the limit of the tower is the limit of this ratio, and we know that Ni is at least 3 to the I, and Gi is exactly this expression, and this limit is 1. On the other hand, the Drinfeld-Pladut bound tells us that the limit is at most the square root of q minus 1, and q is 4, so this is 1. And therefore, there must be an equality, and so this tower is optimal over F4. So we are almost done. Note that we still need to show that all the ramification in the tower occur above rational prime divisors in F0. Remember, this was an additional assumption that we need to justify. So for that, we need to recall the following definition of the ramification locus. So let F be a tower over Fq. The following set is called the ramification locus of the tower, and it consists of all the prime divisors in F0, which are ramified in some extension, Fi over F0. So there are two things to notice here. So first, note that we consider prime divisors of any degree, not just degree 1. So this set is infinite. So the ramification locus is not necessarily finite. The second thing is the following. Suppose that capital P is a prime divisor in Fi, which is ramified in Fi plus 1 over Fi. That is, there exists some prime divisor above it in Fi plus 1, such that the corresponding ramification index is bigger than 1. And let P be the prime divisor in the rational function field in F0, which lies below this capital P. Then, of course, this P belongs to the ramification locus of the tower, since it ramifies in the extension Fi plus 1 over F0. This is obvious. It follows from the multiplicativity of the ramification index. The ramification of capital P hat over P is the product of these two ramification indices. And since the first one is larger than 1, then so is the product. Now remember that our assumption was that if capital P is ramified in the extension Fi plus 1 over Fi, then it lies above P, which is a rational prime divisor in F0. Therefore, since P belongs to the ramification locus, in order to justify this assumption, it is sufficient to show that the ramification locus is contained in the set of rational prime divisors in F0. And this is what we are going to do now. So our goal now is to show that the ramification locus of the tower is contained in the set of rational prime divisors of F0. So in general, it is quite difficult to analyze the ramification locus. Fortunately, we have the following theorem, which we can apply in our case. So what is the theorem? Theorem 6. Let F be a recursive tower over Fq, which is defined by the equation f of y is equal to h of x. And let f be the basic function field of the tower. That is, f is just fqxy, where x is some transcendental element, and x and y satisfy the following relation. Assume that every prime divisor of the rational function field fqx, which ramifies in f over fqx, is rational. So in other words, if we consider the function field extension f over fqx, then all the prime divisors which are ramified are rational. So in particular, if we denote by lambda 0 the following set, so for each prime divisor of the rational function field fqx, each such prime divisor that is ramified in this extension, we add the following element, the evaluation of the function x at p. So know that if we assume that all these ramified places are rational, then p is just either p infinity or p of x minus a for some a in fq, and therefore this value is either infinity or an element in fq. So lambda 0 is contained in the union of fq and infinity. So this is the assumption. And moreover, suppose that there exists another set lambda, which is also contained in this union, such that lambda contains lambda 0, and if beta is in lambda and alpha is some element in this union, and we have that alpha and beta satisfies the equation f of beta is equal to h of alpha, then in fact alpha is not only here, but actually in the set lambda. So under this assumption, if we are able to find such a set lambda, then we can conclude that the ramification locus of the tower is finite, and moreover, it is contained in the following set: the set of all the rational prime divisors of f0, such that when we evaluate the function x0 at p, then we get an element of lambda. So this is the statement of the theorem. Let's try to apply it in our case. So in our case, the tower is T1, and the basic function field is f for xy, where y and x satisfy this relation. And recall, we already saw that this is a Kummer extension of the rational function field f for x, with n, which is 3, and u, which is this element. Therefore, by Kummer theory, we know that if capital P is a prime divisor of f, which lies above P, a prime divisor in the rational function field, then the ramification index is given by this ratio, where Rp is this GCD. So let's see what we obtain in our case. So in our case, n is 3, and u is this element, and we need to check what is this valuation. So note that if we factor the denominator of u to reducible factors, we get that u is exactly this function, and therefore we get that the valuation of u at the place p is as follows. So if p is p0, then it is 3, since we have this 3 in the numerator. If it is p delta, p1 plus delta, or p infinity, then you can check that the valuation is -1, and otherwise the valuation is 0. Now, know that when this valuation is 0, then this is 0, and the GCD is 3, and therefore we get that the ramification index is 1. And also, if P is P0, then this valuation is 3, and the GCD is 3, and again, E is 1. However, when P belongs to this set, then the GCD is 1, and E is 3. So we get that the only prime divisors of the rational function field which are ramified in this extension are these 3 prime divisors, P delta, P1 plus delta, and P infinity. So in our case, what is the set lambda 0? So what is the definition of lambda 0? So for each prime divisor of the rational function field, which is ramified in this extension, we add the evaluation of x at this prime divisor. So in our case, the prime divisors are these 3, and x is this function. So the evaluation of x at the first prime divisor is delta, at the second is 1 plus delta, and at p infinity, it's infinity. So we get that this is lambda 0, and indeed, it is contained in F4, in the union of F4 and infinity. So this assumption holds. Now, what about the set lambda? So we claim that lambda can be taken to be lambda 0, the union of lambda 0 and the 1. That is, lambda is just 1, delta, 1 plus delta, and infinity. And let's see that indeed it satisfies the required conditions. So clearly, lambda contains lambda 0 by definition. So it remains to check that the second condition is also satisfied. So remember, the second condition is that if beta belongs to lambda and alpha is some element in this set, in the algebraic closure of FQ or infinity, and alpha and beta solve this equation, then alpha must be in lambda. Okay, so let beta be an element in lambda, and suppose that beta cubed is equal to alpha cubed over alpha squared plus alpha plus 1. So this is the equation in our case, and we want to show that this implies that alpha belongs to the set lambda. So let us first consider the case in which beta is infinity. Then in this case, it's easy to see that either alpha is infinity or the denominator is 0. So alpha squared plus alpha plus 1 is 0. So alpha is either infinity or delta or 1 plus delta, since these are the two solutions of this equation. In any case, we get that alpha indeed belongs to the set lambda. Okay, otherwise, if beta is not infinity, then beta is 1 delta or 1 plus delta. So in particular, beta belongs to the multiplicative group of F4. It's an element of F4, which is not 0. Therefore, beta cubed is 1. Hence, we get that our equation implies that alpha cubed over alpha squared plus alpha plus 1 is actually equal to 1. And of course, this equation implies that alpha cubed is equal to alpha squared plus alpha plus 1. Now, note that since the characteristic is 2, then alpha plus 1 cubed is exactly alpha cubed plus alpha squared plus alpha plus 1. And the sum of these three is exactly alpha cubed. So this sum is 0. And therefore, we get that alpha is 1, which indeed belongs to delta. Therefore, we see that the set lambda satisfies the required conditions, and therefore we can apply the theorem and conclude that the ramification locus of the tower is contained in this set. And what is this set? It's all the rational prime divisors of F0, which satisfies this condition. So again, a prime divisor of degree 1 of F0 is just P infinity, or Px0 minus alpha for some alpha in F4. And what is the evaluation of x0 at P? Well, if P is P infinity, then this is infinity. And if P is P of x0 minus alpha, then this is just alpha. And we want this value to be one of these. Therefore, we simply get that this is the set of P1, P delta, P1 plus delta, and P infinity. These are exactly the rational prime divisors in F0, such that when we evaluate x0 at these prime divisors, we get an element of lambda. So in particular, we get that the ramification locus is contained in a set of 4 rational prime divisors of F0. In fact, recall that by the previous analysis, we know exactly what is the behavior above each one of these prime divisors, what is the behavior of the tower above each one of them. And we actually saw that above each one of them, there is some prime divisor which is ramified. So in fact, this actually holds with equality. Okay, so this completes the proof that the tower T1 is indeed optimal. Okay, so we showed that the tower T1 is optimal, but now that we did quite a lot of work. We analyzed the behavior of all the places above the rational prime divisor of F0 in each level of the tower. And in fact, we can use another theorem from the class, which saves a lot of work, and we will get the same result much easier. So let's see. So for that, let us first recall the definition of the splitting locus. So let F be a tower over Fq. The following set is called the splitting locus of the tower. So what is a splitting locus? It's a set of all the rational prime divisors of F0, such that P splits completely in all the extension Fi over F0. And notice that here, unlike the case of the ramification locus, we are only considering rational prime divisors of F0. In particular, since this set is finite, the splitting locus is always finite. In our case, note that we saw that the splitting locus of the tower is exactly the prime divisor P0. This is the only rational prime divisor in F0, which splits completely in all the extensions. In fact, we can also show that this set is contained in the splitting locus using an analog theorem for the splitting locus. So this is theorem 8. Let F be a recursive tower over Fq, defined by the equation f of y equals h of x. And again, let F be the basic function field of the tower. And assume that there exists a non-empty set sigma, which is contained in the union of Fq and infinity. So in particular, sigma is a finite set, such that for all alpha in sigma, the prime divisor Px minus alpha splits completely in F. And for all capital P in a prime divisor in F, which lies above this Px minus alpha, the evaluation of y at capital P belongs to sigma. Then the following set is contained in the splitting locus of the tower. The set of all the prime divisor of the form Px0 minus alpha when alpha belongs to sigma. So in our case, we can apply this theorem with sigma, which is the set containing only 0. And in fact, you can use the same argument that we used for the extension f1 over f0 to show that this divisor splits completely in F. And also for every capital P in F, which lies above this place, the evaluation of y at B is 1. So the evaluation of y at this place is 0, which belongs to sigma. So I will leave it for you to check if you want. But this is essentially the same thing that we did when we analyzed the behavior of the place P0 in this extension. So let's summarize. Using these two theorems, we can quite easily show that this set is contained in the splitting locus of the tower, and the ramification locus is contained in this set. Now, using these two facts, we can use yet another theorem. So before we state the theorem, let's recall the definition. A tower is called tame if all the ramification indices are co-prime to the characteristic. For example, in our case, the characteristic is 2, and each ramification index is either 1 or 3. So indeed, our tower is tame. And the next theorem says the following. Let F be a tame tower over Fq with F0 the rational function field, and let S be the size of the splitting locus and R be the following sum. So we go over all the prime divisors in the ramification locus and we sum their degrees. Then it is guaranteed that the limit of the tower is at least 2s over r minus 2. So let's apply this theorem in our case. So we know that in our case, the splitting locus contains the place P0, so S is at least 1. In fact, we also know that it is equal to 1, but this is sufficient. And what about R? Well, in our case, every place in the ramification locus is rational. So the degree is always 1, and therefore R is simply the size of the ramification locus. So R is this size, which is 4. And therefore, we immediately obtain that the limit is at least 2s over r minus 2, and 2s is at least 2. In fact, exactly 2. And the denominator is exactly 4 minus 2, and overall we get 1. So this is another way to show that the limit of the tower is 1. So the tower is optimal. Okay. Note that so far we considered the recursive tower T1 over F4, which is defined by the following equation. Now let's consider the following change of variables. So let's denote by zi the inverse of xi. Clearly, each fi is obtained by adding zi to the field fi minus 1. And moreover, a simple calculation shows that zi plus 1 cubed is, by definition, 1 over xi plus 1 cubed. But now we can use the defining equation to replace xi plus 1 cubed and express it in terms of xi to get this thing. And then just some algebra, we get that this expression is equal to this expression, which is exactly zi plus zi squared plus zi cubed, which again is equal to zi plus 1 cubed minus 1. Again, we are using here the fact that the characteristic is 2. And by doing so, we get that the tower T1 can also be recursively defined as follows. So we defined f0 to be the rational function field over f4 with the variable z0. And now fi is fi minus 1 together with zi, which is recursively defined by the nicer equation y cubed is equal to x plus 1 cubed minus 1. So now this is a polynomial equation, which is nicer. And in fact, with this representation, we can prove a much more general result. So let L be a prime power, and let Q be L to the R, where R is some integer, which is at least 2. And let M be Q minus 1 over L minus 1. And know that this is an integer, since this is equal to the following sum. Then the following equation, y to the m is equal to x plus 1 to the m minus 1, defines a recursive tower T over fq with limit which is at least 2 over q minus 2, which is positive. So in other words, this theorem gives us a construction of a tower which is asymptotically good over fq, where q is some non-prime field, since R is at least 2. And remember, by asymptotically good tower, we just mean a tower whose limit is strictly positive. Notice that the tower T1 over F4 that we considered is obtained by taking L and R to be 2. And indeed, in this case, we get that the limit of the tower T1 is at least 2 over 4 minus 2, which is 1. So this result is much more general. The proof is a bit more difficult, but essentially you can show it using the same tools, the theorem about the ramification locus, the theorem about the splitting locus, and the following theorem about the lower bound for lambda. So I will leave it for you if you want to try it yourself. It's a bit more challenging, but it's nice.